circuit. In this part of circuits, we're going to introduce two types of circuits, single loop circuit and multi-loop circuit. And three rules that apply to both single loop circuit and multi-loop circuit. And also we're going to introduce a rule that applies only to multi-loop circuit. In the end, we're going to introduce a very significant circuit that's called RC circuit. It is significant because we are pivoting from this point from what's important as current to what's important as time, RC constant. Single loop circuit here, we have three examples. If you start from the positive side of the battery, you can go all around the circuit and goes right back to the battery in one single path. Loop rule. Loop rule is different than Ohm's law. Ohm's law applies to a resistor. Loop rule applies to a circuit. So that's the different conditions, which says, for example, in this loop, the total change of electric potential when you go all around a circuit is 0. This is similar to, for example, if you run a course. If you run a half marathon, a marathon, from your starting point to where you start, you're getting back to the same point. The total change of height is the same because however much you go up, you will go down. So here is the same. In the same circuit, when the electric potential goes up, it'll eventually come down. In the end, the total change is 0. Loop rule applies to both single loop circuits and multi-loop circuits. It applies to any loop. Look, it's called a loop rule. It's not called a single loop rule. EMF. This is a historical word, and here it just represents a power supply. That could be a battery, it could be a wall plug, it could be an adapter. EMF rule. Some of these power supplies power the circuit. For example, in this circuit, epsilon B powers the circuit so that the current flows the same direction consistent with this power supply. But if you look at epsilon A, it's actually opposite the direction of the current. So it's being charged, or it's absorbing electricity, absorbing energy from the circuit. So in this circuit, the potential through epsilon A drops of E of A, and the potential through E epsilon B increases. Resistance rule. Just like water always flows from a higher place to a lower place, electric current always flows from a higher electric potential to a lower electric potential. So along the direction of the current, the electric potential always drops. So this is what we call the resistance rule that helps us understand and know how the electric potential changes through a resistor. Grounding a circuit. So the ground, or say the earth, is considered a really, really, really big object, and it can contain a lot of charge. Overall, it's neutralized. So if we connect any device or any circuit to the earth, we consider that connection point to have electric potential of a constant. This constant potential, we define it, or just mathematically call it, give it a numerical value, call it 0. For example, so like the height. The height, we can define height relative to the sea level on Earth. We can define height relative to the ground level at a certain place, or we can define 0 height relative to the lab bench surface. So the height is always defined in the reference system. So is the electric potential. Grounding, let us define the electric potential relative to the earth, and the earth is always defined as 0. It is always safe to add physical grounding to a equipment to let out excess charge, and also to keep it safe for both people and equipment. This is an example how the electric potential changes throughout the circuit. From point A, how it's gonna be not changing until it reaches epsilon 1 through the wire. It doesn't change through the wire. And then through the epsilon 1, the power supply or battery, it drops because here, from A to epsilon 1, it drops. because that's opposite the direction the current goes. And through little r1, it increases a little more because we're going against the current. So if we apply the rules, we can understand how this chart works. So this chart can be also read from right to left, starting from A on the right, and then we go along the direction of the current. So the direction of the current, epsilon 2, is actually opposite the direction of current. So it drops epsilon 2. And then it drops through I times R2, little r2. And then it drops I times R along the direction of the current by the resistance rule. Then it drops I times little r1 along the direction of the current by the resistance rule. And finally, it goes up by epsilon 1, which is by the EMF rule. Example of loop rule. So here we solve a particular problem with the loop rule. It's asking us what the current is. Remember, we do not apply Ohm's law here because we have a complete circuit. When we have a complete circuit, we apply loop rule. When we have a single isolated resistor, we apply Ohm's law. Although sometimes the two have a little bit of overlap, some of the problems sort of can be solved by both, but it is actually rigorous to start from the loop rule for a loop. Here's an example of battery. What's interesting about a battery is that it usually has what we call internal resistance. So that's a small amount of resistance that always goes with a battery, because a battery inside it needs to have wires, and wires always have resistance. So this is an example. Little r is a resistance and is part of the battery, as you can see in the shaded area. So that's the internal resistance. Okay, we introduced a single loop circuit and 3 rules. Those 3 rules apply to any loop, actually. And here we introduce a particular multi-loop circuit. So in this circuit, if you see between R1 and R2, there is a point that's connected to 3 wires. So that is what we call a junction point. So you can see in this circuit, we have more than 1 loop. So how does junction rule applies? It says the sum of the currents entering any junction must be equal to the sum of the currents leaving the junction. So do we know which direction the current flows by looking at the circuit? Sometimes we can tell, sometimes we cannot tell exactly, but we can always just draw the direction of the current and solve this circuit. After we solve the circuit, sometimes the current turn out to be negative. What does that mean? That means the current actually is in the opposite direction. You can either count it as a negative current along this direction, or you can flip the direction of the current and so that it'll flow the other direction. But anyway, we can tell whether the current flows into this point. For example, C is a junction point. So for junction point C, in this case, we have 2 currents flow into it and 1 current flow out. So in this particular case, the total amount of current flowing in equals to the total amount of current flowing out. Next, what if for some circuits, what if in the case of another circuit similar to this, and I2 turn out to be negative? Well, in that case, we know it actually flows out of C. So for that case, we can either count it as flow into C as a negative value or flow out of C as a positive value. We're actually going to use this in the lab. So here's an example of a junction rule. So verify the junction rule. Actually, this is a lab assignment. We're going to add 3 meters next to point C, immediately next to point C. And in the lab, when you add the meters, use a wire between the meter and the resistors. Don't add the meters directly to the resistor, either for simulation or for real instrument. Find out the total amount of current entering point C and find out the total amount of current leaving point C and indicate if they're the same or not. We can do this in the lab for simulation or for real instruments. Okay, our third topic is RC circuit. On top, we see a circuit with only resistors. At the very bottom, we see a circuit with capacitors. what if we combine resistors and capacitors? Historically, this is a significant circuit that brings us from the focus of current to the focus of time or frequency or timing or signals or information. So this is the very, very beginning of using circuit to express information. Charging circuit. What's a charging circuit? So if we close the switch, the electric power supply will charge the capacitor. So capacitor voltage will go from 0 to a certain value, in this case, V of S. So when the voltage becomes from 0 to the power, the same as the power supply, we call that the capacitor is charged. After that, even we remove the battery, the voltage will remain on the capacitor and charge will remain on capacitor. So that is to say, if you take out of a cabinet in the lab a capacitor, be careful because the capacitor, although it's not connected to a power supply, it can be having charge and can be having electric voltage. And be careful when you touch that capacitor. So what happens when it charges? If we write the equation using the loop rule, so here we're actually applying the loop rule. So the power supply V of B minus I times R minus Q over C, which is the voltage, equals to 0. And then so we can turn this into a differential equation. By solving the differential equation, we can find out that the Q or the charge, which is represented by the red colored curve, goes up slowly and fast and then slow down and eventually it approaches the constant value of capacitance times the voltage. So this is how the total charge works. And we have also an equation, Q equals to C times V, 1 minus E negative T over RC. RC, R times C, 1 ohm times 1 farad equals to 1 second. And if you look at the horizontal axis, it's 1 RC, 2 RC, 3 RC, and 4 RCs represent different time intervals. At 1 RC, the amount of charge equals to 63% of the total charges. And also we look at the current. What happens to the current? The current is represented by the dotted line, and the dotted line actually decreases. And when eventually the capacitor is fully charged, there's no more current. So current stops flowing. And at 1 RC, the current is reduced to 37%. If you just apply 1 RC, T equals to 1 RC, then T over RC equals to 1. So that's 1 over E. That's how you plug the number into the equation. RC discharging. So if we remove the battery and just connect both sides of the capacitor through the resistor, this circuit on the lower left corner represents discharging. Discharging means removes the charges, which means the positive charge and negative charge from both sides of the capacitor will neutralize. If we look at the voltage function as a function of time, when T equals to R times C, which is in the unit of second, then the voltage is reduced to 37%. It takes a couple of RCs for the voltage to become negligible. So sometimes if you find an isolated capacitor, it can also be not charged at all. Maybe it's discharged. So if we don't know of capacitor isolated, can be charged, can be not charged. In summary, we introduced single loop circuits and the 3 rules that applies to any loop, including loop rule, EMF rule, and resistance rule. We introduced a multi-loop circuit, and the junction rule applies to circuits with a junction. That's what we call multi-loop circuits. In the end, we introduced a very significant RC circuit. It's so important because it helps us to transition from focus on current. The more current, the more motion, the more heat, the more light, and the more sound, to information. RC represent a time, and we can use this to eventually understand the more complicated, more sophisticated circuits that we use for modern communication. So RC circuit is a significant pivot point in this class.